and it's time to look at strlen. If you were thinking about our previous videos, you might have the same question as the author of the Stack Overflow question had, or as I had at some point, which is how can strlen read multiple bytes at a time, given that, the whole point of strlen is we don't know how many bytes we have, we're trying to find out. There is an awesome answer by Stephen Cannon, who wrote a macOS implementation of strlen, and we're going to look at my version of that answer. Basically, as you know, allocation happens in pages, which means that if you have 1 byte, the whole page where that byte is belongs to your process. You don't know what's in that page, but it is yours to read. We also know a couple of things about pages. We know that the page has at least 4 kilobytes of size. There are no systems, at least I'm aware of, that support pages less than 4 kilobytes. And we also know that when the page is allocated, the beginning and the end of the page is aligned to the size of the page. And, which means it's aligned to 4 kilobytes. Because size of the page is bigger than equal than 4 kilobytes, it means that, if it's aligned to bigger numbers than 4 kilobytes, then it's going to be aligned to 4 kilobytes. Okay, which means that if you take an address somewhere that you own, you can find the next place that can be potentially the end of the page, right, by finding the next address aligned to 4 kilobytes. And this is an important insight. It means that till the end of the page, we can read in whichever sizes we want. We can read by 4 bytes, by 16 bytes, whatever. It all will work. It's actually used in many different C-strings algorithms. However, strlen, we can do a more special thing. Let's have a look at the previous aligned address before S. Right? I'm going to use a register size 32 bytes. So let's have a look at previous address aligned to 32 bytes. What do we know about it? Well, first of all, since the beginning of the page is aligned to 4 kilobytes at least, right, the previous address aligned to 32 bytes is not going to be before the beginning of the page. It means that reading it, will not crash because of this, right? We also know that the end of the page is aligned to 32 bytes. It means that the distance between our aligned S and the end of the page is divisible by 32. And which means if we go looking for zeros by 32 bytes in one go, then we will either have the ability to load the entire 32 bytes, or we will not be able to load, or we'll be able to load none of 32 bytes, means we are here exactly, right? Basically what I'm saying is, if you want to load 32 bytes, and you can find the previous aligned address and load 32 bytes from there, and that is always safe. Okay, let's use this to implement strlen. We're going to forget everything about pages. We're going to take S, we're going to take previous aligned address, and we're going to load 32 bytes from there. Now, using intrinsics and some SIMD instructions, we can write a quick implementation that will check the 32 bytes for zeros. However, if there were any zeros between aligned S and S, we're not interested. Like there might be previous string here, and those would be misleading. So we need to skip that. This is why all of the reductions like this will support some form of ignoring certain elements. Okay, so we're going to check this first bit for zeros, skipping this between aligned S and S. After that, we will just check for zeros. We don't need to do anything special. The first zero will work for us. Here there is no zeros, and here there is a zero. We will get the position, and this is going to be our answer. Okay, let's have a look at version of this code written with if. Since it loads. So, this is strlen, with underscore, accepts const char star, returns size t. First thing I'm going to do is I'm going to interpret cast from const char star to, uint 8. The reason is that const char star is not guaranteed to be either a signed char or an unsigned char. Like it's not guaranteed to be signed on unsigned EU int 8. And it means it's very uncomfortable to work with. So in if we only support int 8 or U int 8. And the next thing I'm going to do is I'm going to declare a type def for if wide of U int 8t. This is a type in if that represents a register. By default, if we don't provide a size, it will choose size native for the current compilation options. In this case, it's going to be 16. That's the way it's compiled at the moment. All right. We're going to need some zeros. And as we discussed, we're going to find the previous aligned address, load from there, test for zeros, cur equal zeros. This returns you, well, in this case is 16 chars, so this is going to be like 16 Boolean-like values, right? We're going to find the first true out of those 16 Boolean-like values, ignoring whatever we had to before the first character actually belonging to the string. And then, while we didn't find any matches, we're going to go to the next register, load it, and test it. Okay. Finally, we have to do some conversion between, where we stopped and what the actual function should return. Okay. I think it's an interesting exercise to look at macOS implementation of strlen discussed in that Stack Overflow post. I'm going to copy this as the main loop there. So, okay. And we're going to do 1, 2, 3. Let it compile. Okay. What do we see? They do compare SIMD equal. We do SIMD equal. We do move mask B. We do move mask B. We do test and then jump. Test and jump. So we are doing effectively the same thing as they do, right? The order is slightly different. They've written it in a little bit a different way, but this is the same code, conceptually at least. Okay, there's a little bit. We'll talk about this later, but actually the strlen should be written with if in a little bit different way, and I don't want to leave you with like an incorrect piece of code. Like basically, as far as assembly goes, there is no difference, but there's this if unsafe around if load. We'll talk about it some other time. And we're going to do benchmarks now. This is benchmarking with a different libc, a glibc. This is libc from from Linux, my Linux box, and I'm actually compiling not with 16 bytes, but I'm compiling with this option, which tells that the compiler that in the library that my machine supports 32-byte registers and more powerful SIMD instructions, because this is what the standard strlen uses, and it makes our fight more fair. Okay, first result is for 40 bytes. Right, we can see that the even on 40 bytes, the while loop, right, is about 8 times slower than the standard strlen, right? And we are a little bit faster than the standard strlen, I suspect purely due to inlining, right? Our code can be inline, standard strlen cannot. Now, let's go to 1000 bytes. This is the example I used as a motivational one. Right here on my machine, the standard strlen was about 35 times faster than the while loop. It's 250. This is 7, right? Our strlen is a little bit slower than the standard one on 1000 bytes. And on 10,000 bytes, our strlen is significantly slower, like almost twice as slow than the standard strlen. So clearly there is something else we can do, right, to improve our performance. We'll talk about it the other time. Finally, you can find the code of strlen that we discussed in if examples. I'm gonna load. Yeah, it has the exact implementation we looked at Godbolt, only with comments. Okay, and that's it for today.